Are you able to hear me?
Yes, you are audible.
Okay, thank you. So, good afternoon,
Yes.
everyone. Welcome to the week 11 live session on finite element method. I'm your TA Danish Bashir from Structural Engineering Division, Department of Civil Engineering, IIT Madras. So, in the last week, we saw that how we can put all the problems that are the general in case of fluid flow or heat flow or conduction. We can have a general boundary value problem for all those kinds of applications. And in last class also, we saw the formulation for the fluid flow between two plates. Like for between two plates, how we solved the problem for the fluid flow between two plates, which were separated by a distance h. So continuing on the same topic, today we will be seeing one more application of this general 1D boundary value problem, that is the column buckling. In column buckling, you might be aware of this topic of column buckling from your strength of materials course, wherein we study the column buckling, where we have different conditions of and conditions for a column. Like we have a fixed column, we have fixed one and fixed and another and pinned, and we have one and fixed and another and free. All these conditions we studied in structural this strength of materials course. But in finite element analysis, we can also study that column buckling as well. But here we can include, as I already mentioned, that we can always include complex geometries as well as complex boundary conditions. So today we will be seeing that what complex geometries and complex boundary conditions there can be in column buckling, and also deduce a formulation for column buckling using this general 1D boundary value problem. So start. So today let us start today's lecture with the topic column buckling. So let's consider for column for the calculation of a buckling load of a column. Let's consider a simply supported column. That is, it's pinned from both the sides. Like we always have a notion of showing the columns in a vertical direction like this. But let me show today column which is like this, horizontal, is the same column, uh, and let's its support conditions be it's simply supported from both ends, simply supported from both ends. Okay, this end it is simply supported, and this end also. Okay, these are the boundary conditions for our column. Okay, so an axial load P is acting. So load P is acting on this column in this direction. Okay, what else is that there? So this column can have a deflected shape like this, because we already know what will be the buckled shape of this column, because this is pin joint. So buckled shape will be like this. So I have to draw it a little bit. So buckled shape will be like this. Okay, this is the buckler shape of our column. Then what else is there? This column is having a transverse displacement, like it will be having displacement in this direction. Okay, let us denote that displacement by W. Okay, and this column is having a total length of L. Here, total length is equal to effective length because this is pin jointed column. Okay, L, and let EI be constant for this column section. Okay, all these things we have given. So this is the case of a simply supported column. Okay, we have a case of a simply supported column. So let me write the governing differential equation for the problem, which is of order fourth and which can be stated as follows. Governing differential equation. Governing differential equation for column buckling. Column buckling is this d2 by dx square ei d2 w by dx square, second derivative of the transverse displacement, plus p times d2w by dx square. I'm not going into the derivation of this differential equation because this has been derived from the first principles, which it's very easy. You have to just consider the equilibrium of this column section and use the this curvature relationship, moment curvature relationship. We can easily get this equation. Okay, and in this is the Young's modulus. Young's modulus. I is the moment of inertia of column cross section. Moment of inertia of column cross section. Okay, and W, it's important to note here that W is a transverse displacement. Okay, all these things are there. So if we are considering our like this EI to be constant here, EI to be constant here, then this EI can be taken outside of this differential, and we can have an equation like this. We will have EI is taken outside, d power 4 W by dx power 4 plus p times d2 W by dx square is equal to 0. Okay, following this, the boundary conditions for this simply supported column will be the boundary conditions for column, it's simply supported. Okay, boundary conditions will be, so transverse displacement at x equals 0 is equal to transverse displacement at x equals L, both are equal to 0. You people can easily see that here it is x equals 0, here it's x equals L, here W is also equal to 0, and here also W is equal to 0. Please note these points. Okay, also this is simply supported, so moment generated at these points, so at this point and this end it will be again 0. Okay, so another boundary condition that we will be having, that is moment curvature d2w of 0 by dx square should be equal to d2w of L by dx square. Both are equal to 0. Okay. So if you clearly look at these boundary conditions, this is essential boundary condition. Essential boundary condition. If you look at the nature order of the boundary condition, okay, this is natural boundary condition. So all these things are given. So this problem can be converted to a second order differential equation if we make some substitutions. Okay. So let's make the substitution. Substitute. We will put y is equal to d2w by dx square. Okay. Once we will make this substitution we will make in this equation. Okay. Here. Okay. So we will have our equation will reduce the differential equation will become second order. Okay. So our differential equation will become ei times d2y by dx square plus py is equal to 0. So we got a differential equation which is of second order. Okay. Second order. Now again the boundary conditions here will be boundary conditions. We will follow the boundary conditions will be again y of 0 will be equal to y of L will be equal to 0. Okay. It's from this boundary condition. This is actually y of 0. This is actually y of L because y is equal to d2w by dx square. I hope you people are getting this point. So for this dividing throughout by ei, okay, we will get d2y by dx square plus p by ei times y is equal to 0. Okay, and the boundary condition is y of 0 is equal to y of L is equal to 0. Okay, so if we do one thing, we will compare our this equation. We will compare this equation with our general 1D boundary value problem. We will get the following quantities. So again, I will take this general 1D boundary value problem for your correspondence like this. Sorry, this should not be okay. This, if we copy it from here and go to our slide, this is our this one. Okay, we will compare it with it. So comparing with this equation. Okay, comparing with this equation, what we will get variable in general form. Okay, and corresponding variable in column buckling equation. Column buckling differential equation. Okay, so if you people can clearly look at this thing, k is equal to here 1. Okay, k is equal to 1 here, k is equal to 1. Okay, because it's 1 times d2y by dx square, it is k times d2t by dx square. So k is clearly equal to 1. K is equal to 1. So what we are actually comparing, we are comparing d2y by dx square plus p by ei times y is equal to 0. We are comparing this with this. Okay, to get the values of k, p and q. Okay, and clearly looking at p, we can see that P is equal to, like here it is, P is having the definition of load in this. So P is general, use it in a general sense here, P of T. So T is here, here it is Y field variable. So P by EI is equal to actually P of X. So this P of X, let me write, K of X is equal to 1, P of X is equal to P by EI, okay? And clearly if you see that here it is q of x, here is no other term is in plus further, so q of x is equal to 0. I hope you people are following me. So we made this correspondence. So this is a table that is very important, okay? Okay, this table you need to remember, okay? Then using the we know that what is the uh, I mean to say that elemental equation solution for general 1D boundary value problem. Using all these values 1, p by ei and 0, we can get the two node element of length L can be written as follows. So I will write here using general form the finite element equations for two node element of length L can be. So we know that it is given by 1 by L, then its matrix, it's 1 minus 1 minus 1 1, matrix close, y1 y2 y1 y2, okay, then it is minus PL by EI, it is 1 by 3 1 by 6 1 by 3 1 by 6 1 by 6 1 by 3 y1 y2 y1 y2 is equal to 0, okay. So this is the finite element equation for a two node element for our column buckling problem. So in the whole equation, we are not having the value of p. P is unknown. So if p is unknown, then this becomes an eigenvalue problem, okay? You will get this concept clear once we solve a numerical problem on this column buckling. So let's consider today's first problem is one. Okay. So for example, we have a column, simply supported column, simply supported from this side, okay. We have roller supports from this side. Sorry, this should be circular one. Okay. These are the two things here. Okay. Then what we have to do is we have to use a four number of elements. So the total length of the column is L. We have to use four elements. Okay. This is one, this is two, this is three, and this is four. This is L by four, 2L by four. This is 3L by four. This is L. Okay. So we have to use four number of elements. That is element one, element two, element three, element four elements for this column, which is having x is like this and y is like this, and it is subjected to some actual load p. We have to find this buckling load p for this simply supported column. Okay, so the finite element model for this is, so this is four element finite element model. Okay, we have to use this four element finite element model for this. So our first node is here. So this is our first node, this is our second node, this is our third node. Okay, so this will be node first, this will be node 2, this will be node 3, this will be node 4, this will be node 5. Okay, I hope this is clear to you guys. Node 5, node 5, node 4, node 3, node 2, node 1. Okay, so we have to solve this simply supported column which is subject to an actual load P. We have to find this load P that will cause the buckling in our column. That is, we have to find the buckling load. So we have to use this element equation. For each element, we have to write equation using this, and then we have to find the load. Okay. So let us start. So the element equations are, okay, element equations are, since this L is equal to L by 4, because the length of each element is L by 4. So 1 by L is will be equal to 4 by L. Okay. So first thing will be 4 by L, 1 minus 1 minus 1, 1. Okay, y1, y2, y1, y2 minus will be PL by 4EI, 4EI 1 by 3, 1 by 3, 1 by 6, 1 by 6, 1 by 3. Okay, y1, y2 is equal to 0, 0, 0, 0. Or this equation can have a form. We will take 4 by or we will take 4 by L common from here, 4 by L. Okay, then this is here, so this will be 1 minus 1 minus 1, 1, y1, y2, y1, not y1, y2, so y1, y2 also will be common. Okay, so this will be directly, when you take common, you will get PL square by 96 EI. Okay, so you have taken 4 common, so you have to divide by 4 also. Okay, so it will be 4 3 are 12. Okay, it will be 2 here, it will be 1 here, it will be 1 here, it will be 2 here. Okay, just simple algebra. Y1, Y2. Okay, Y1, Y2 is equal to 0, 0. This is okay. So 4 by L can't be equal to 0. So this whole is equal to 0. Okay. So I am just erasing 4 by L from this. Okay. So after the assembly, so since this will be the common for each element, sorry, each element will be having this equation, same equation. So we have to assemble all these four equations together to get the global system of equations. Okay. So after assembly, after assembly, the global equations are okay. Global equations are as follows. So the global system will look like somewhat like this. Okay. So we will be having first one large matrix like this. It will be 1 minus 1. Then there will be three zeros. Okay. Then we have minus 1, minus not 2. This will be minus 1. This will be 0. This will be 0. Then this will be 0. This will be minus 1. This will be 2. This will be minus 1. This will be 0. This will be 0. This will be 0. This will be minus 1. This will be 2. This will be minus 1. This will be 0. This will be 0, 0, minus 1 and 1. Okay, we got this matrix. Then we have our common PL square by 96 EI. It's common for everyone. And we will be having one more matrix like this. And it will be having entries 2, 1. And then there will be three zeros. 1, 2, 3. And we will be having 1, 4, 1, 1, 4, 1. We'll be having double zero. Then another entry will be 0, 1, 4, 1, 0. Another entry will be 0, 0, 1, 4, 1, and this will be 0, 0, 0, 1 and 2. This is this, and this closes like this bracket, and this is y1, y2. Not y1, y2. This will be y1, y2, y3, y4, and y5 up to y5 because we have four number of elements. So there will be five nodal unknowns. Okay, everything is 0, 0, 0, 0, 0. Okay, so this is our global system of equations. Okay, after applying the boundary conditions, so boundary conditions are y1 equal as y5 equal as 0. So I have told you the thumb rule. So y5 is equal to 0, and so fifth row and fifth column will wipe out, and again second row, first row and first column will wipe out because y1 and y5 are equal to 0. Okay, so it will wipe out from this also. Okay, this matrix also. Okay, so I will write the reduced system. I will write the reduced system, and one more thing, I will make one more substitution, that z to be equal to p l square by 96 ei. Okay, otherwise I have to write it again and again. So once I do all these substitutions, I will get a reduced system like this: 2 minus 4 z minus 1 plus z, 0. Then I will get 1 minus 1 plus z, and another one will be 2 minus 4 z, minus 1 plus z, then 0 minus 1 plus z, and last one is the 2 minus 4z. Okay, y2, y3, y4. We have to find the value of y2, y3, y4. Okay, and it will be 0, 0, 0. Okay, we have to follow this system now. Okay, so we have to get the value of the we have to get the eigenvalues for this matrix first. Okay, this matrix we have to get the eigenvalues. Okay, because this is the eigenvalue problem, we have to get the eigenvalues for this. So for to get the eigenvalues, set determinant to be equal to 0. Okay, so we will write the determinant of this 2 minus 4z minus 1 plus z, 0 minus 1 plus z, 2 minus 4z, and minus 1 plus z, 0 minus 1 plus z. This is 2 minus 4z, and its determinant is equal to 0. So once you will solve this determinant, you will get an equation 4 minus 48z plus 108z square minus 56z cube to be equal to 0. Okay, so the three roots of this cubic equation will be z1 equal to 0.108, comma z2 equal to 0.5, and z3 equal to 1.32. So what these eigenvalues say give us, actually these eigenvalues give the I mean to say that, for example, if there is a lowest eigenvalue, this lowest eigenvalue will give the first buckling mode of our column. This second eigenvalue, second highest eigenvalue will give the second buckling mode of our column. This third eigenvalue will give the third highest more third highest eigenvalue will give the third buckling mode of the column. So since we have to see the lowest root, this lowest root will correspond to the first buckling mode, and that first buckling mode we will get our P critical or the buckling load. Okay, so I will write here for you people the lowest root, the lowest root corresponds corresponds to the first buckling mode, to the first buckling mode for the column. Okay, okay, thus the buckling load for the column is buckling load will be, so for z equal to 0.108, so actually z is equal to PL square by 96 EI. Okay, now P here will be replaced by PCR is equal to 0.108. So which implies that PCR will be equal to 0.108 times 96 EI by L square. Okay, when you solve this, you will get the PCR value to be equal to 10.37 EI by L square. Okay, okay, this is the solution. Okay, so we will see how much is the theoretical or the theoretical value of this critical load or the buckling load. So we know that theoretical theoretical buckling load is given by the formula PCR is equal to You people know it. It's pi square EI by L square. Okay, L square. Pi square is actually equal to 9.87 EI by L square. Okay, this is theoretical. Okay, so this is very close, 9.87. Theoretically, we got 9.87, and finite element we got 10.37. So there is little bit of error. So this error will be minimized. So there is almost 5% error. So the error is almost 5%. Okay. We also have to find the buckling mode for this column. Okay. So this buckling mode is nothing but it is the eigenvector corresponding to the eigenvalue z equals lowest eigenvalue. Okay. So we can find that also. So let me write that the buckling mode can be determined by finding the corresponding eigenvector. Okay. Vector as follows. Okay. So substituting z to be equal to 0.108, we will get the global system of equation to be equal to 1.568 minus 1.108, 0 minus 1.108, 1.568. This will be minus 1.108. This will be 0 minus 1.108. This will be 1.568. So we have to find the value of y2, y3, y4. y2, y3, y4. Okay, that will be the mode shape. Okay, 0, 0, 0. Okay, so for this, so arbitrarily we will select y2 to be equal to 1 and solve for y3 and y4. Okay, when we will put that one, we will get our y3 to be equal to 1.411 and y4 to be equal to 0.997, and y1 and y5 are already equal to 0. Okay, so we got our values, these values are very important because they correspond to the first buckling mode. Okay, so let me write one more thing is y1 equal to 1, y5 is already equal to 0. Okay, then so the lowest buckling mode is, our lowest buckling mode will be then equal to y will be equal to 0, 1, what the values we got, 1.411, 0.997, and 0. So transpose what it actually means I will show you. So for example, if this is the column so y is equal to 0 here, so it will be point here, y is equal to 1 here. So this is y1, this is y2, this is y3, this is y4, this is y5. So if y2 is equal to 1 here, so this is equal to 1, and this is y3 equal as 1.4, 1.411. This is y4 is equal to again 0.997, and this is 0. Then we have to draw a line which passes through these points. Okay, this is the first buckling mode. Okay, first buckling mode of column. Okay, so we can improve the accuracy of our solution if we use a higher number of elements, that is two elements, three elements, four elements, five elements, six elements. We already use it four elements. It can be increased accuracy can be increased if we use five elements, six elements, and seven elements respectively. Okay. So this was the column buckling. This was very important so far as finite element is considered. I hope you people got the concept of column buckling. If you people have any questions, you can ask. Then we were seeing only two noded elements, that is lower order elements. There are higher order elements for one dimensional problems as well. So actually what we have to use for our problem, we have to use higher number of this lower order elements to get the better results. But if we use higher order elements, that is the polynomial of our element is of having higher orders, quadratic, cubic, or fourth quantic, that's fourth order. We can use a lower number of elements for solving our problems. So we had shear functions for lower order elements where we assumed linear trial solution for our element solution between the two nodes. We can have quadratic solution between the two nodes. Okay, we can assume that one, and then we can deduce the shear functions. I think this higher order elements and Lagrange interpolation function and all these things we will study in next class, as we don't have that much time right now. So I think this enough for today. Thank you, everyone. If
Okay,
you
thank
people
you.
have any, if you people have any question, you can ask.
I want to check that how many more classes would be there.
There will be one more class, week 12, and there will be one more extra class on 15th. I am taking
Okay,
one
okay.
more extra 15th April.
It will be
Okay.
on 15th. 15th. Okay, okay.
Yeah.
15th would be Monday, right? Then
Yeah, Monday. That's on Monday. And
Monday.
before that, the Saturday that's coming, we have week 12. Okay.
Yeah, right, right. Got it, got it. Thanks.
Okay.